So we will discuss today about unit third. Unit third of atomic and molecular physics, atomic molecular and laser physics, and it is mostly the whole unit is about molecular spectroscopy. Molecular spectroscopy. So up to now, what we have discussed atomic physics and atomic spectroscopy. So in this third unit, we will not go into molecular physics actually, the structure of molecules, the formation of molecular orbitals like HOMO, LUMO. That detail we don't need here. We'll only study the basics of molecular spectra. And molecule, you all know that a molecule can be defined as, simply you all know this definition, that a molecule is actually a bound system of electrons and one or more than one nuclei and more than one nucleus. So when you have more than one nucleus and bound system of electrons, then that whole system, that bound system, is termed as a molecule. Like you can have, say, H2. It is a bound system of 2 electrons, 2 nuclei. Like you have carbon dioxide. It is a bound system of 3 nuclei. And this is 8 plus 8, 16 plus 12, 28 electrons. Okay, so this is how we define a molecule, and it is actually a combination of electrons and more than one nuclei and a number of nuclei. So in this chapter, we have to discuss the different range of energies, in which the spectra of molecules is observed. The spectra of molecules is observed, and in how many ways a molecule can emit this some energy, or they can form an spectra, and what is the process of this emitting these different energies, then giving the corresponding spectra. So the mainly here in this unit, we have to discuss different energies and spectra of diatomic molecule. So we will we will take a special case of diatomic molecule, and it can be a homonuclear or a heteronuclear. Homonuclear, this is homonuclear, this is heteronuclear, this is a triatomic actually, like carbon monoxide is a diatomic heteronuclear molecule. So we will take a case of this diatomic molecule, and we will also study the spectra as a result of vibration, rotations, and electronic states, electronic energies, vibrational energy or rotational energy or electronic energy. So that means when the spectra is observed between by the transitions between vibrational energy levels, we will get vibrational spectra. Similarly, when spectra is observed when there are transitions between the rotational energy levels, so it will be a rotational spectra, and when there is this transition between the electronic energy levels, so that will be an electronic energy. But before that, let us see that what are the different energy ranges. So we will see that what are the different energy ranges which are responsible for vibrational, rotational, and electronic energy, the spectra. So in what energy range these spectra fall? So what is the range of the energies for vibrational spectra, rotational spectra, and electronic spectra of molecules? So electronic spectra, you know that there's a transition between the electronic energy levels as we have done it in unit second. That is in atomic physics. We take the atoms, transition between different atoms, the energy levels of the different atoms. So we are ignoring at that time the rotation and the vibration at all. So first let us start from vibration, then rotation, or simply let us start from the electronic. So we all know that to study a given molecule, any molecule, whether it be a homonuclear molecule or a heteronuclear molecule, it's a diatomic molecule or a triatomic molecule or is a polyatomic molecule of any number of atoms. When you have different atoms or same number, multiple number of atoms, then the structure of the molecule, and hence the spectra of the molecule becomes a bit complicated. It becomes difficult.
Sir, repeat.
So what I say is that when you have multiple number of atoms, more than one, more than two, one, two, three, more than two, one means two, three, four, five. Then you have nuclei, you have electrons. Here I will see the nucleus. For example, if this is the case, this is simplest case. Let this be carbon, oxygen, oxygen. Carbon. These are the internuclear axes. So we have many number of electrons. You have more than one nucleus. And to study this system, you need to study the interactions between nuclei. You have to study the interaction between nuclei and electron. You have to study the interaction between electron. So these all interactions make it a little bit difficult to completely study this system. Or in other words, I can say that it is not easy to solve the Schrodinger equation for the whole system that you all know, and we have already discussed it in previous classes. So to solve these systems in general, when we treat many body problem, when we take many body examples or many body systems, we make some approximations. And the first and the foremost approximation, the first approximation or the most important approximation being that is called Born-Oppenmeier approximation. That is called Born-Oppenmeier approximation. We will discuss that approximation in detail a bit later, but at this stage, at present, we will assume that the motion of this is one of the postulates of a Born-Oppenmeier approximation. The motion of nuclei is much slower than electrons. So that means, because at any particular given temperature, all the atoms in a system, they are in a continuous state of motion. That means nuclei is also in a state of motion without giving it some external energy. That means that we are not giving, but at some particular temperature, at some particular instant of time, so they are in a continuous state of motion. And in that state, the nuclei is much slower than electrons. So from this, we conclude that nuclei nearly occupy a fixed position. within the molecule. So they are moving actually, but they are moving slowly, very slowly, such that they can be treated as fixed. Nuclei can be treated as fixed. So let us suppose that we have a given molecule, and this molecule has two nuclei. This is a diatomic molecule, and if there is an average distance between these two molecules, it is A. Okay, then from uncertainty principle, you know that delta X, delta P is approximately equal to H cut. Now here the position is, it is A, this distance delta X, delta P is approximately H cut by A. So at any given temperature or at any given instant of time, the kinetic energy or the energy of the molecule is its kinetic energy, and this energy will be from, if this is a nucleus, these are external orbits, you have these electrons, inner electrons, you have outer electrons. So which among these electrons will be in a state of higher energy? Since these are the inner electrons, these are bound. These are outer electrons, these are valence electrons. So valence electrons are almost free. They are free. We treat them as free electrons or valence electrons. And these electrons can have higher kinetic energy as compared to the inner electrons, as compared to these, because these are bound. These are bound, these electrons, inner electrons. So when they are bound, that means they cannot be disturbed much as compared to these electrons, these here, by any external perturbation. So that means these valence electrons possess higher kinetic energy, or the energy of the atom will be given in terms of these valence electrons. These will be solely responsible for any energies which are involved in the atom, because these electrons are closely bound to the nucleus. They will not move. They need very large external energies to be made free. So they can be made free. But these electrons need very small energy, and they are in a continuous state of motion. So the total energy of the atom will be directly proportional to these energies of these electrons, these valence electrons. What I mean is valence electrons. So I can write then the energy of the system, this atom, is the electronic energy, the energy of these electrons, these. So that is how I write EE. It is P square by
2m.
2m. So when I write it as P square by 2m, so I will use the value of that P, this delta P actually, in a small volume. So I can write it as this 2 is a constant, so it is approximately proportional to this factor. Okay, because I have here using this value, uncertainty value. So from this we can see that this EE is I know that, but what we are taking actually due to the small dimensions of the molecule, we calculate its energy at any particular position, because they are related through the Heisenberg's uncertainty principle. So the momentum, magnitude of the momentum at that any instant of position will be given by its uncertainty. And in this case, EE will be, these are the rough estimates. We are not calculating the exact estimate. These are the rough approximate estimates. So we will calculate the approximate values, a rough value, a rough estimate of the energies. What will be the order of magnitude? I will not calculate the exact energy of any given system. So what I calculate, I am calculating the approximate estimate of the order of the magnitude, or simply the order of the magnitude of the energies. So if you calculate this, h cut square by ma square is a constant factor here. These turn out to be that approximately equal to the order of few electron volts. If you put up the value of h cut in terms of electron volt, and a take a equal to 1 angstrom approximately. This is between two nuclei. 1 angstrom is 10 raised to power minus 10 meters. Okay, so we take these approximate, and m is the mass of the electron. So when you take the mass of the electron and h cut square and a equal to 1, then you will find that this h cut square by m simply, and put up the value because it's in angstroms. Calculate h cut in the angstrom and m in the angstrom, then you will see it's a mass. So you can use it in kgs as well, no problem in that. And use with h cut by m, it will be the unit of energy. So the final unit will be in energy in electron volts, and order of few electron volts will be the result. And this is approximately equal to the binding energy of electrons, these binding energy of these electrons. Okay, so this means that the electronic energies of molecules lie in the range of UV and visible regions. So the few electron volts, that is the range of the UV energy region spectra, UV spectra, and the visible spectra. So those energy ranges are of the order of electronic energies of the molecules. So this is one case when we have a simple electronic energies. We have simple electronic energies of the molecules. Now suppose that you have a molecule. This is a molecule, and it is connected by some internuclear axis and imaginary axis. And I will ask you that what are the different possibilities of the state of the motion of this molecule, how we can move this molecule apart, because in electronic energies we are not treating any motion of the nucleus or the molecule. What we consider only that we have a molecule and it is stagnant, it is steady at a position, some position there, it has some position with respect to the origin, with respect to any origin it is fixed, for example. But in reality those are actually, there can be other possibilities. We can give some energy such that the molecule can rotate about an axis. We can give some external energy such that the molecule can rotate about its some axis, any of the axes, internuclear axis, an axis perpendicular to this nuclear, or like this, which is perpendicular to both, okay, or here. So it can rotate about any axis by giving some energy. It can also vibrate. We are giving some energy to a molecule and it vibrates. It can vibrate inverse towards each other. It can vibrate away from each other. Okay, so these are different types of motion. Or there is another motion which is called translations. We have a molecule, so it can be flipped. It moves from particular position to another position, moves to here. It can move from this position to this position. So it is in a one directional motion, so it's a translational motion. So we can have different types of motions now within a molecule. So we can have a vibrationals, we can have rotationals, we can have translations. And accordingly, the spectra will be classified. We can have a rotational spectra, we can have vibrational spectra, we can have translational spectra, or sometimes we have the combination of rotation and vibration. So that is called rotational vibrational spectra. We will see them in the later classes. So these all spectra will be studied in state of equilibrium. So we'll first take the molecule in the equilibrium state. We'll take a molecule in its equilibrium state, then give some energy so that the molecule can vibrate, so that the molecule can rotate, or the molecule can have a translational motion. And we know the range of energies in which the molecule vibrates. We have the range of energies in which the molecule can rotate, and people study the spectra because these spectra, rotational, vibrational, or these simple electronic spectra, these all depend upon the internuclear axes, the binding energy between the electrons and the nuclei, the internuclear forces, with what forces the two nuclei are connected to each other. So any change in those internuclear axes.
सर आप बहुत तेज बोल रहे हो.
Okay, let me take it easy. So यहाँ तक ठीक है कि ये रिपीट करना है कुछ?
At equilibrium position, what type of motion the particle has?
हाँ बोलो, फिर से बोलो.
Sir, at equilibrium position,
look,
ये तीनों motions हो सकते.
At equilibrium, actually the motion, there are molecules, atom is continuous in a state of motion. It can have a rotational, it simply has a vibrational motion. Some nuclei vibrate with respect to their own axis. Some molecules, they can have a vibrations with respect to the internuclear axes in the equilibrium position. And when we give some external energies, the molecule goes into the excited state, like an atom. Okay, because any atom in the molecule, we cannot treat it as a completely stationary. Practically, it is not completely stationary. But what we do, we do some approximations. We take some approximations. So when we start from something, that means when we start to give some energy to the molecule, before that we treat it in the equilibrium. For example, if it is a molecule, we are not giving any energy. So it may be in a state of motion, but it is equilibrium state actually, because it will be continuous in a state of motion, and that will be treated as it is equilibrium state. Whenever you give some external energies, it will gain more energy. It will gain more energy, and now the transitions will change. The energy range in which this molecule may emit the radiation, that will change, because once you have an atom in the ground state, it is in equilibrium state. You apply some energy, electrons excite from this level to another level, and they come back, then emit the energy. So that energy directly proportional to the spacing between these two electron energy levels. Now in the molecule, these depend upon the molecular energy level separation, because there are the energy levels of the molecule now. Those will not be treated as the energy level of an atom. They will be treated as the energy levels of a molecule. Because any state, when you are not perturbing it, you are not giving any external energy to it, is it equilibrium state? When there is no external force, that it is this equilibrium state. Whenever you give some energy, then it is not an equilibrium state. It is excited to some it is shifted to some higher energy state. So at some instant of time, or at any particular instant of time, a molecule is in a state of both. It may be in a state of rotational motion, or it may be a state of vibrational motion, or it can have a both. But to study them, we need to first study them individually. We need to study them individually. And for that, we have to separate them. Separate means we have to separate the translation motion from the vibrations, translation motion from the rotationals, because they can, at some particular instant of time, they can have all the motions at once when you give some external energy. So to treat them, to study them theoretically, we will take them one by one. We will not combine all of them. First, we will, to study their magnitude, to study their order of magnitude, we will treat them individually. And for that, we will use some approximations. The first approximation we will do for separation of translational motion by taking the center of mass approximation. In center of mass approximation, if you have different number of atoms to form a molecule, when you have different number of atoms to form a molecule, then we will use some approximations. The approximation is center of mass approximation, and when you have a molecule, you take some center of mass. For example, it is here. For example, so you take this molecule as a single particle. This molecule as a single particle, and it becomes a single free particle in the absence of some external field. Then instead of these two atoms, we have a single molecule with center of mass somewhere here. And now the translation motion is absent. In a single molecule, we will not see the translation motion. Because translation motion, it shifts us. This is a molecule, it will move to some external position. So it will reach here, then go here. Now it will become a single particle. It will become a single particle. So when it becomes a single particle, the translation motion is now treated as independent. There we can see that there is no translation motion when we study the vibrations or the rotations. So this is just an approximation for studying the different energy ranges. Now from here we will see that we will take an approximation in which we will consider that now the molecule has only vibrations and rotations. So what I am saying is that because a molecule at any given instant of time, I have to repeat this. So I'm repeating it. You have two different atoms. This is center of mass axis here. And it can translate. Translate means that it can translate itself. Itself means it was here. Now it shifts from here to here. And at the same time, it can vibrate. Or at the same time, it can have a rotation. So that to study this rotation, vibration, or translation at the same time, it becomes difficult for us. To make it easy, we will make some approximation. And we will treat all the motions independently, separately. So when we treat these motions separately, we have to make some approximations. And the first approximation is used for separating the translation motion to make the molecule free of any translation motion. That is only possible when we treat these two molecules, these two atoms as a single entity. How is that done? That is done by taking the center of mass approximation. So it becomes a single molecule now, single atom, a single particle actually. To get rid of the translation motion. And up from here now, we can take now the vibration and the rotation. Because we are not taking any translation motion here. We will be taking now only the this vibration and rotation here. Let us take the first example, first case of vibrations. Suppose that a molecule is vibrating, but it is vibrating as a linear harmonic vibrator. molecule has linear harmonic vibrations with angular frequency omega n, because vibration means nucleus is vibrating. This is an atom, this is an atom, this has a nucleus which is heavy, which is very heavy. These are electrons here. When a molecule vibrates, that means this nuclei vibrate, and they vibrate with an angular frequency of omega n. For example, if nuclei and these nuclei, they have some equilibrium distance, now they move a distance apart. They move from their equilibrium positions and a distances, they vibrate. That means it was here, so it moves here, this can move here. So they move distance a from their equilibrium position. Let this be a, this be a. The vibrational, the distance in which it vibrates, it is a. So what is the vibrational energy then? E. I will take m mass of the nucleus. M omega square a square, because energy is equal to 1/2 of m.
Omega square square.
Okay, this m is the nuclear mass. I will write mn. Nuclear mass. Because of vibrations, if molecule was at a particular distance, at equilibrium distance x equal to 0, it moves now to x equal to a. So when you move an object from one point to another point, it stores some energy in it. That is a potential energy. That is a potential energy. So that energy is given by 1/2 mn, and it will be E vibrational actually, because it is because of the vibrations of the molecule.
Actually, is there a kinetic energy of these particles?
No, it's a potential energy now, because it was initially at rest at some this position. We have moved this against some this binding force between the two nuclei, because they were attached to themselves by some binding force. So when you drive, when you vibrate them, that means you are displacing, you are dissociating the molecule. It was initially in some state of energy, ground state energy. We are dissociating a molecule from particular position here to and shifting to here. How will it vibrate? You have a spring. This is a spring. How it vibrates? It vibrates like this. It can vibrate. This side goes in and this side goes out. Okay? Or this side comes in, this goes out. These are the possibilities. Okay? So when we take that molecule is vibrating, these are moving apart from each other, or they're coming close to each other. You are simply doing, you are dissociating the molecule. You are separating the molecule. You are moving one nuclei away from the another. Are you getting me?
Sir.
Yes, sir.
Okay, so that means we are actually dissociating the molecule. So that means we are separating the nucleus from the electrons. Is it okay?
Yes, sir.
We are separating the nucleus from its electrons. And then that means this energy, the energy of dissociation, or the energy with which we are moving the nuclei apart, becomes approximately equal to the electronic energy. This becomes approximately equal to the electronic energy. So I can write then m omega n square a square is equal to h cut square Is it okay? Or there is some problem in this. So what I am saying is that means when a molecule vibrates, that means one of the, take a simplest case of diatomic molecule, 2 atoms. Take a simplest case of 2 atoms. So these are vibrating. So what can you do? You can take 2 atoms in 2 hands and just push them close to each other. Or take 2 atoms in 2 hands and just move them apart from each other. This is how they vibrate. Is it okay? Do you understand what I'm saying?
Yes, sir.
Okay, so when you are moving them close to each other, are you moving them apart from each other? You are just moving the nuclei from apart from their electrons. You are dissociating the molecule actually. You are separating the nucleus from the electrons of surrounding those nuclei. Do you understand? If anybody has a confusion, he can still say it. There is no issue. I will not move ahead. So is this equation okay? So in that case, the energy with which we are moving the nuclei apart from each other is just because equal to approximately, not exactly. These are the approximations.
Electronic energy.
The dissociation energy of the molecule. That is the we are moving. That is the electronic energy of the molecules. And we can write this expression then. So we can write then energy, vibration energy. What is it equal to? H cut omega n. Because it is vibrating now. So we have the vibrational energy, the vibrational frequency in terms of the vibrational frequency, that is angular frequency, that we can write h cut omega n. This is the lowest mode of vibration. Lowest mode of vibration. And I can write it as, if you take omega n from this equation, this 2 and 2 will cancel. What I can write here, I will write here from this, take this equation. So m omega n square a square is h cut square by m a square. Keep omega n here. This is nucleus, this is electron, so don't confuse with each other. H cut square omega n, we have to h cut, no, not this equation, we are taking this equation, yes, this. So h cut square, m will go denominator, a square will go into denominator, and we have m already there, a square already there. So, or I can write omega n square is approximately equal to h cut square divided by mn a4, or omega n will be approximately equal to I can write it as equal to h cut divided by under root of m into a square, or I can write it as equal to h cut by a square. Okay, I can write it as m the root of m.
Yes, sir. 100 m by m.
I'm just taking the approximate value to get the order of magnitude, and it can be written as h cut square divided by m into a square. Is it okay?
M by m, 1 by 2.
But it is e this.
सर एज कट स्क्वायर नहीं
H cut, yes, this is H cut. So it implies that the vibrational energy for the lowest mode of the vibration is approximately equal to E times this value, m by mn. And if you see, this is of the order of few electron electron volts, 1 electron volt, 2 electron volt, 3 electron volt, this. Okay, and this value, this is mass of the electron to the mass of the nuclei. Mass of the nuclei. This ratio is equal to 10 raised power minus 3 to 10 raised power minus 5. Okay, and when you take under root of this, it becomes even smaller. It becomes even smaller when you take under root of this. And that means that the vibrational energy is much smaller than electronic energy, and it is of the order of 0.1 eV. Rough case, in order estimate, that is approximately. So it is smaller than those electron volts, few electron volts. It is a fraction of the electron volts, or the energies of the vibrations. The vibrational energy of a molecule is smaller than the electronic energy. This can be said in another way, that if you have an energy level, this corresponds to the electronic transition. That means an electron can do a transition from this level to this. There is some vibrational energy here, energy level. When a molecule vibrates, it emits a small amount of energy. So that means giving a small energy to the molecule, it can vibrate, and it can go from this lower energy state to this. When it comes back to the ground state, this energy from electronic energy transitions, it is of the order of it is of the order of few electron volts, but this is of the order of 0.1 electron volts. So that means the vibrational energy is very small as compared to the electronic energy. Okay, this is another point. Now let us see what happens when the molecule rotates. Take a simplest case of diatomic molecule. We have a diatomic molecule. It is separated by some nuclear distance a, and it moves with some rotates with some angular velocity omega about an axis. This is atom A, this is atom B, for example. Then it has a moment of inertia when a molecule rotates. Moment of inertia axis. Then the energy of this molecule is given by E equal to h cut square by 2I. There is an L actually. There's not that. There's angular momentum actually. It's not orbital angular momentum here in case of molecule. It's not conserved actually like in the atom. And it's a constant actually. It is L into L plus 1 here. It is for the case.
ज़्यादा हो रहा है।
यस सर, आज इतना ही पढ़ेंगे।
आज इतना ही पढ़ोगे, मुझे कोई प्रॉब्लम नहीं है। फिर बाद में बात कहना कि सर ऐसा स्पोर ही नहीं की।
सर
So this ER is h cut square by 2I, and this I is equal to 1 by half of mr square actually. R is A here. So I can write it as 2I, 2 into 1 by 2 ma square. Or I can write it as h cut square into m divided by m into a square into, sorry, I will multiply by small m. So it is EE times m by m. And this value comes out to be 0.001 eV, which is very small as compared to the vibrations and this translation. So in general, I can write and another thing is that the nuclear rotationals, they take much time as compared to this electronic rotationals. That means the time periods for the nuclear motion are very, very large as compared to the time period for the electronic rotationals. So that's why we can treat electronic motion and the nuclear motion independently in some cases. We can make that approximation. Okay, so this is all for today. Just see it again at home if somebody has written it. And I have to cross check one point here. Let me do it. Here we have a problem. So EV, this is omega n, this is E, omega n. So it is h cut divided by m into A. So this is what we have calculated actually omega n here. It is h cut omega. So you have already h cut there. This is h cut square by A under root m. This. Then ER, this EV, vibrational energy. That is h cut omega. So that is equal to h cut into omega is this much. And there is another h cut. So this is how it becomes actually h cut square here. So there's this h cut multiplied to omega n. So then it becomes h cut square. That's how it becomes EE. So h cut from this and h cut in already in the omega n. So that will make it h cut square. So that is EE. H cut square by ma square. And similarly, I have used that value here. H cut square by ma square, that is EE. And the general representation is that EE is greater than EV is greater than ER. So if you want to draw the energy level diagram, so you have somewhere these electronic energy levels, this E dash, then you have vibration energy levels in between them, then you have rotational energy levels. So remember that this is EV dash, this is EV, this is ER dash, ER, this is ER dash.
सर बोर्ड लैग हो रहा है.
I will not move from here. Is it okay? What we have
Sir,
stated so far. What we have stated so far. From that, we can conclude that electronic energy levels have a large energy range as compared to vibration and the rotation. So one point is common here, that whenever there is a vibrational motion, there will be a rotational motion. You cannot avoid a rotational motion from the vibrational. From this ER, it lies in between the vibration and the electronic. So that means when you have an electronic transition, because they need much more energies, you can have this rotational as well as the vibrations. Similarly, when you have vibrational motion, you can have rotational motion as well. And then we take some approximations and treat them independently. That is another case for solving it, for simplifying these things. So I will leave it here and just see it at home. Just check it at home.